Hello all newcomers and welcome back fellow Eternians. My name is Emperor AP. Today, as always, I am going to be doing a live stream. Specifically, many of you know I am in school right now. I'm going through a degree program. And so I am going to be studying special relativity. Trying to get through some homework and just some understanding the concepts from a course that I'm in. So this might be a little bit boring for some of you. For some of you it might be interesting if you like science, but I'm going to be going through that and just talking about it, breaking down some of the general concepts, and ultimately trying to prepare myself for upcoming tests and material. So I'm going to go ahead and get into that. But one of the things I wanted to let everybody know, right now I'm having difficulty with the comments, so I may not be able to see your comments for a second. I'm going to try and see if I can figure that out. I hope you are all doing well. I see we have 2 viewers right now. What's going on, guys? Let me see. Let me see if I can fix this. Are you guys able to put things in the chat? Because I'm not able to see the chat right now. Hold on. So right now I'm going to turn off the live chat, and then I'm going to turn it back on. Enable live chat and see if that'll get it to work. Let's see if it brings it up. There we go. Hey, what's going on, Royland? How are you? We are doing special relativity right now. I'm trying to get everything set up and started. As well, I just went to the store and I got some ciabatta rolls. So I am going to be getting started into studying special relativity, and you all can sort of join along with me. This is going to be one of my first bigger study sessions for special relativity. It's a small course at the university compared to the material that's in other courses. It's kind of an introduction, but it does go into some of the math, and it does sort of give you a good feeling for what special relativity is. And so I'm going to be going through and studying. If my whiteboard here doesn't fall down, and hopefully I can teach you all something along the way. So that is what we are up to. Let's see. So one of the first things that we learn about in special relativity is the idea of, give me just 1 second. Is essentially that there are variations within different inertial reference frames. So we have this idea of inertial reference frames, just meaning that there is a specific, with each moment in, let's say we're measuring in time. In each moment in time, we are dealing with one specific inertial reference frame. We are dealing with one energy, we are dealing with one momentum, we are dealing with one force, if that's what we're measuring. We're dealing with some consistent form or shape that this energy takes. So that being the case, as we measure through time, we notice that these things, they can be observed differently depending on your reference frame. So what I mean by that is we talk a lot in physics about the speed of light, and that's something that if you become interested in physics and you learn more about it, or if you hear an astrophysicist or something talking on TV, you might hear them describe the speed of light as a constant throughout the universe. It's how we measure a lot of things. It's how we come to understand a lot of things on both very, very large scales and very, very small scales, because it's one of the things that is the cornerstone of this relativity. We find essentially in very extreme cases, the reason this is called special relativity is because in extreme cases we have these fundamental laws of physics, these Newtonian laws that we learn about in our earlier physics courses, essentially Newton's laws, you can go and look them up yourself. Every action has an equal and opposite reaction. Those sorts of building blocks, and then eventually getting into electromagnetism follows a lot of that. But once we get into really, really small detail and focus on something, or really, really large scales like galaxies, we notice that some of the time these laws that we like to believe are always true are not. And so that's where we get into these inertial reference frames. We are trying to classify a better way to, we're trying to find a better way to classify the information that we're receiving from different measurements, from different reference frames. So we're saying that we have the speed of light, which is constant throughout the universe at all scales, at all distances, and throughout all inertial reference frames, which is just each moment in time having that specific energy pattern, having that specific whatever you are describing, heat, electromagnetic radiation, force, momentum, velocity, acceleration. That all of these things are set through time. In fact, velocity and acceleration are functions of time. You cannot have velocity or acceleration without measuring it through unit time. Let me go ahead and see if I can check the comments here. I believe I can see them now. So I'm about to start getting into actually solving some problems. Hey, what's going on, Republic of Greenia? Like I told them, we are doing a homework live stream. So if you can't follow along, don't worry about it. Just hang out and talk to us. Okay, we are going into the idea of watch time. So when we talk about inertial reference frames, and when we talk about these needing to find these constants, because if you have a very, very large object, well, let's not start there. If we have something that's moving really, really fast, right? We said the speed of light is a constant throughout the universe at very large scales, at very small scales, at all distances, in all ways. The speed of light being that constant, we can then say, as things approach the speed of light, weird things start happening, and we notice that through our equations. The thing that we start to notice is it's not just at the speed of light that this is happening, but in fact happening in all inertial reference frames. But we will get further into that in a moment. Ultimately, this acceleration that you're having, not acceleration, excuse me, this velocity that you're having, if you're moving through some medium, moving near the speed of light, what we notice is that for different reference frames, for different observers, things may happen at different time scales. So if I have a watch, this is the famous concept of watch time, or there's another term for it that we learn. It is, I believe it's standard time, and that is sigma naught, I believe. So we're going to write some equations down here in a second, but that's what we are going with. So let's see here. There we go. It's called proper time. So watch time, or proper time, essentially is the idea that we have some, a rock that we strap a watch onto, like a wristwatch. We strap that wristwatch to our rock, and we sling it out into the universe at nearly the speed of light. If we have a group of people that are observing this, if we have one person that is passing it in a spaceship, and we have another person that's passing it in a plane, and we have another person that's passing it in a car, and we have another person that is standing still, And we also have another person that is flying with the watch, actually holding on to the rock or moving at the same velocity as the rock. What we notice, and in fact I'll illustrate this, what we notice is that all of these observers get different lengths of distance per unit time. So let me break down a little further what that means. Like we said, we're going to have our big rock here. It has our watch on it. And through time t, we are, through distance, let's say we are measuring through distance. Through distance L, we are measuring watch ticks. We have one person who flies with the rock at velocity v. We have one person who's over here at some velocity w, or v2. Let's say v2, right? We have another person over here at velocity v3, so on, so on, so on. What we'll notice is all of these people will get different measurements for how long it should take for those seconds to go by, for those watch ticks to go by, if we can all observe the watch. Let's say we're filming it and we can instantaneously transfer that information or something. Let's say we can all look at the watch as it's passing by for some reason. That being the case, what we're able to say here is that if we know that the speed of light, which we're going to denote as c, is, I believe it's 9 times 10 to the 8th meters per second. It's something similar to this. It's a very, very large number, but we're going to denote c as equal to 1. That's how we denote it in Special Relativity. But the idea that I wanted to get by writing this number out is simply this meters per second. This is the speed of light, so it's the velocity. The velocity is the distance traveled divided by the amount of time it takes to travel that distance, or every meter, how many seconds, or every so many meters equaling 1 second. That being the case, we can measure time as a unit distance, or distance as a unit time. That's what we do here. Because we end up being interested in making these observations, we're all traveling at different velocities, but we need to have something that is constant, and what is constant we can figure out is the speed of light. So we have this one observer who is going with the rock, right? Let's say at velocity v, v1, right? We have observer 1, observer 2, observer 3. So observer 1 would notice that the ticks happen at what they should, some fraction of 9 times 10 to the 8 meters per second. So he knows exactly how far he's traveled. So he says, hey, I hit this distance in 1 second. Every second I go this distance. So my ratio here is 1 to 1. I am able to know that this is the proper time, or watch time, that is connected to or associated to this event, which is this watch traveling at some velocity v. Now, that being the case, we want to say, well, we would like to be able to use that for many different things. For example, there is another concept that we will look at here in a second. Let me see what the equation for proper time is. Give me just 1 second. Yeah. Okay, so what my textbook is saying is that our proper time, which is equal to t, that watch time that we talked about, the time that is equal to the time that you would have as you move along with that projectile, with that thing moving near the speed of light. So we have this proper time tau squared is equal to our time delta t minus our change in position x squared. Let me double check that. Yep. So, what's up, man?
Did you know you left the freezer open?
Oh, no, I didn't. Oh, right on. It must have just been for a second, huh?
And it's defrosted some stuff.
Yeah, so getting back to this, we have our proper time tau squared equals our change in time squared minus our change in position squared. And all of our observers do agree on what this value is. So the way that we would solve for that and figure that out, if we're dealing with our rock with the watch on it, is that we would first take the value that the person with the rock gives. So they would say tau squared is equal to delta t, let's say, okay, delta t minus delta x. So if the delta t is a change of 1 second, so 1 second squared would be 1 minus change in x squared would be 1, squared is 1.
Do you need anything?
1 second, guys, 1 minus 1 being 0. So we're going to hold on to that tau. Give me just 1 second. So,
Yeah, I looked in. I thought it was open. I'm like, I don't need anything like that. You can see. Yeah, should be fine. I don't think there's long. Cool. Did you get paper plates or just paper towels?
I got paper plates and folders.
Was that $8 included?
No, I don't have.
Yeah. Oh, yeah, I just need to pick up a set.
No, that's not a big deal.
Just tell me how much it is when I get back in. If you want to later get off it.
See you, Matt.
See ya.
All right, I'm going to go ahead and check the comments, see what you guys are talking about before we jump back in. Republic of Grania said, wait, what are we talking about? Socialist Republic of Lagos said, hey, Grania. Socialist Republic of Lagos said, Grania. Republic of Grania said, hi. Awesome. So nobody's talking about the special rel homework. All right, I see how y'all are. Okay, so we're about to get back into this. All right. So that being the case, we say we can do. Let me grab a resource of mine. I'll be right back. Okay. Okay, so this is a good way to think about this proper time concept. Is we're going to go ahead with another thing. So this is the twin paradox. So let's see. Perfect. So we have an astronaut. Let's say we have an astronaut who has a twin, right? So one of the twins grows up, becomes an astronaut. They're going to do an experiment. So the first twin gets into a rocket, right? And says that he's going to fly from Earth to some planet P, right? So he's flying there, and it's going to take him a distance of, hold on, it's going to take him a delta t of 3 years to get there, because he's going to fly at faster than the speed of light. Let's say somehow he can do that. That being the case, his brother ages 5 years. So 5 years have elapsed on Earth. How much time has elapsed for the astronaut? I did make one mistake in my description here. So what this isn't actually delta t, this is delta x. Now the reason for that is because what we're saying here is that 5 years go by on Earth in time, delta t is 5 years. A change of 5 years happens between when the brother leaves and when he gets to this planet to his brother on Earth. So when he gets there, he sends a message to his brother on Earth, and the brother says, it's been 5 years. The distance in light years is 3. So our delta x is equal to 3 light years, or 3 years. That being the case, how much time has elapsed for the astronaut? So what is our proper time? What's the time that happens, not relative to the speed of light, not relative to our observer on Earth, but relative to the person on the spaceship that's going that fast, faster than the speed of light? What is, how much faster are they going? What is the amount of time that's elapsed for them? The way that we figure that out is we solve for our proper time, tau. So we say tau squared, remember, is delta t squared minus delta x squared. Or tau squared equals, remember, what did we say was our delta t? 5 years. So 5 years change in time squared minus 3 years change in time delta x. Or 3 year distance, remember, because it's 3 light years, and light years is a certain amount of distance. How much distance will light cover in 1 year's time? So that is 3 light years here. And then we will put 3 years there, squared. Remember, all of these terms are squared. So we have tau squared is equal to 25 years, because years squared, because we always square our term when we square a number here. So we have tau squared is equal to 5 years squared minus 3 years squared, which is going to be tau squared equals to 25 square years minus 9 square years. and then tau squared equals 25 years squared minus 9 years squared. You do tau equals, and you subtract 25 minus 9, and you end up with 16 years squared. There we go. And then we say that's tau squared is equal to 16 square years. And then we take the square root of both sides. The 16 years square years, and we end up with tau equals 4 years. So, our proper time that our astronaut experienced, even when his brother experienced 5 years on Earth waiting for him to get to that planet, even though it took light 3 years to get to that planet, he experienced 4 years. So what does that mean? Well, that means, first off, I was incorrect. This means that our astronaut was going under the speed of light. I thought he was going over, but looking back at my notes and solving this, we found that he was actually going under the speed of light because it took light 3 years to get to the planet. It took 5 years for time to elapse between him going from the Earth to the planet. It only took the astronaut 4 years in between these two values to get to the planet. So that we can conclude is the fractional percentage of the speed of light that he was going is 3/5 the speed of light, or 3/4 the speed of light. So delta x over tau equals 3/5 c. Perfect. Okay. So now we're going to continue and talk more about all this. Let's see what everybody's saying. Okay. Comments are blowing up out here. Whoa, comments are blowing up. Okay. Trying to find things that are related to this work, but everybody's talking about micronations or something. Awesome. Okay, so I am going to continue back on this work. I hope you guys are having fun. Alright, let's see here. So, I just did that one. Sorry, this is now an eating live stream. Welcome to the eating live stream, you guys. So one thing I need to mention as well, this proper time is something called an invariant. The speed of light, as we noticed, well, I shouldn't say that. This delta t, this tau here is an invariant. That is our proper time. That's the time that is passing relative to the inertial reference frame we are measuring through. So, that being the case, that is our origin, essentially. That is how we, that's the reference frame that we choose to put ourselves in when making these measurements to assert as a constant. So, that's what tau is. Now tau is called an invariant, and that's something that we're going to look for more, is as many different ways to have things that are the same between all inertial reference frames, which will ultimately give that tau. Also, for those of you who aren't familiar with special relativity is the thing that Albert Einstein worked on and is well known for, among many other things. But this is one of the things that he worked on, and I'm excited to be studying it. Or at least starting to get the first grasps on it, you know? Okay, so it is actually delta tau squared. It's not just tau squared. Delta means change in. It's actually the derivative of. So when we say delta tau, we just mean the change in. So if we go from 4 miles per hour to 6 miles per hour, the change in velocity, our delta v, is not 4 or 6, it's 2, because we went from 4 to 2, so we started at 4, went up, we started at 4, we went up 2 to 6, so our delta v is 2. And in the same respect, that's how we do our delta tau here. It's not 9. This is just a correction on my part. C is 3 times 10 to the 8 meters per second, not 9. So, and that's approximately, you know, they have calculations that get better and better, but this is 3 times 10 to the 8 meters per second. That's approximately the speed of light. But in special relativity, to make things simpler, we say that that is equal to 1, and that's what we do. So if we were to say that we needed to figure out a certain amount of, you know, how far does light travel in a second? We say that it's 1 second over 3 times 10 to the 8 meters. So travels 3 times 10 to the 8 meters every second. And that goes the same, you can solve 4 seconds. It would be 1/3 times 10 to the negative 8 as would be solved for. But like I said, in special relativity, we say C is equal to 1 for most equations and solve that way, because we can, it just makes our math simpler, essentially. Taking C equal to 1 also reveals symmetries in equations, which is important for talking about time dilation. excuse me. This bread is delicious, but very dry. Getting back to special relativity. All right. I'm just reading through your comments right now. I hope y'all know I'm watching. I'm out here. I hope y'all are doing well. Also, I want to say we are getting really close to 925 subscribers. That's, you know, inching closer and closer to our 1,000 mark. We are at, I believe, 921 as of right now, so definitely help us out, try and get that up a little more. I would really appreciate it because I am so excited for what we're doing. We're getting up to that 1,000 subscriber mark. We're going to start being able to get funding for the channel. It's going to be great. But getting back to this, let's see. Okay, so we are going to define the Lorentz factor, and that's something that we will go ahead with right now. So we're going to keep this up here because it becomes important later, but we are going to erase our previous experiment here. Thank you to the twins that helped us with it. So we're going to be talking here about the Lorentz factor. So essentially, we can say this, that if we know that delta tau squared equals delta t squared minus delta x squared, and that is our proper time, we can say here that this is the same thing, as I said a moment ago, as the derivative, be kind of that curly d right there, derivative of tau squared equals the derivative of our time squared minus the derivative of our x squared. And what we come out to with that is we can say, actually, we're going to get rid of all this because that'll stay the same as the derivative, but that'll stay the same. So we're going to just carry that on, and we will say that what if we want to find out what it is with respect to velocity? So we can say we could divide both of these. We could do the derivative of t to both of these, and we would end up with, let's see, hold on. We would end up with one squared minus the velocity squared, because remember we said our delta t is the same thing as our derivative of t. So derivative tau is the same thing as delta tau, and that's the same thing for our t and our x. Derivative and delta mean the same thing, they mean a change in. So that's what we're doing, is we're taking the change with respect to t over the change with respect to t, which gives us 1, square that, and then we're getting the change with respect to x over the change with respect to t, and the change in your position over your change in time is your velocity. How fast you can go, how far you can go within a certain amount of time is your speed, your velocity v. So we denote that as script v, and then we can solve that to say 1 equals our velocity v squared, and that delta tau or derivative tau squared equals this. So then if you wanted to, you could keep solving for that. So you could go ahead and say, actually, I'm sorry. So we're not doing that. We're doing effectively the same thing, but it's going to look a little different. So we are doing that. We're taking the derivative of both of these, and that's how we're doing that. So we're saying delta tau equals the derivative of both of these, which is going to become 1 minus our velocity, like we said. So our delta tau equals 1 minus our velocity squared, which then means that you can, let's see what we're doing here. Right, we end up with d of t 1 minus v squared equal to delta tau squared. So what we end up being able to do is take the square root of that on both sides to get that the change in tau is equal to so first we can figure out that gamma, denoted like this, it's kind of like a Y shape a little bit. Gamma is equal to 1 over 1 minus our script velocity, v, and that's all square rooted. So then we can figure out that our derivative of tau is equal to our derivative of our time over the gamma that we just found. Okay, so what this is telling us effectively is that we have this thing. It's called the Lorentz Factor, and what it is doing is allowing us to, in all inertial reference frames, describe our proper time and figure out what that is and how it is affecting your measurement. Let's see here. So, the Lorentz factor was introduced because this quantity appears practically everywhere in relativity, and it's a lot easier to write than gamma than, and they put another equation in there. Well, they essentially put this equation in there. So essentially they say, hey, when we write equations to make things simpler, we're going to include this gamma. Just know that this gamma means that, and that you can solve for the rest of your equations that way. So anytime you have to make adjustments, anytime you have to figure out for certain.
So odd.
What?
I said so odd. Are you live streaming?
I am. I'm live streaming homework. My roommate's here.
Hi.
Yeah, do you want to do special relativity? That's the stuff Einstein was for.
I know, me and him didn't get along. He stole my ideas.
Oh, then you did that. Perfect. That's perfect.
Aha!
See you, man.
Don't tell me I lose a lot.
All right. Okay. Let's check on our comments out here. All right. So. Awesome. We are getting into it. So we're going back to this stuff. We're talking about our rocket trip. Okay, we figured that out. Since gamma is always greater than or equal to 1, we see that the time that has elapsed for you you who is watching the clock fly past, is always greater than or equal to dilated time that has elapsed for the watch. So essentially, what that's saying is that this time that you have elapsing is give me just 1 second. I need to add something to the description. Okay. One of the things I wanted to mention as well, because I needed to bring it up for all this. I just added it to our description. Essentially, I don't own the rights to the material that we're using here. I'm working on my homework, and I'm using a book that was provided to me through a class. So I'm wanting to make sure that I give proper credit where credit's due. I'm not trying to profit off this material or anything like that. I'm just talking to you all while trying to work on my homework. So I'm really trying not to say much about what's in the actual text other than using concepts. So then, let's see. Proper distance. So they describe something called proper distance, which essentially amounts to saying delta. This is a symbol that we call sigma, I believe, equals delta x squared minus our delta t squared. So if we remember, our proper time, delta tau, is equal to delta t squared minus delta x squared. Now the role is reversed. This is our proper distance. Our proper distance is our delta sigma squared equals delta x squared minus delta t squared. And let me double check that that's sigma. I believe it is. I believe it is a sigma. Yep, it sure is. Awesome. So, going back to what we were talking about, let's see how long we've been streaming. 49 minutes. We're going pretty good. All right. Okay, so our delta sigma, like we said, is delta x squared minus delta t squared. So that's our change in position minus our change in time. Whereas before with our our proper time that we had with respect to our moving object in the same inertial reference frame as our moving object, we said that our change in time minus our change in position gave us that. So how long in time it took minus the distance that was the distance that happened in. And those will both be measured with the same value. If you measure it in distance, in distance meaning in meters, they both have to be in meters. If you do it measuring in seconds, you have to have it in seconds. So, or days or years or whatever it is you're dealing with. Whatever your units are have to be the same, because this is going to come out into one single unit in that way. So our sigma is our proper distance, and it's the same thing. Our change in our position squared minus our change in time squared. So we will get into that here in a second. Proper length, proper distance, also called proper length. Cool. So we are given an example to go by. Oh, also, thank you very much for the like. I always appreciate it, guys. Make sure to like and support the video. We always appreciate it. All right. So we're going to be talking about essentially what this is saying is, so our delta tau there can describe a change in time in some way or another, a change in time. So what does that really mean? Well, that means that our change in time for our time that it takes for our proper time, the time that that two objects experience, the time two objects experience can be different from one another. And that describes the same thing in our proper length or proper distance, is that two lengths can be physically different from one another based on how space is affected. And that's where we get the term space-time. That's how we get the idea of measuring and understanding things as values in space-time, because that space-time is what's described here. This space, which, this time, excuse me, which can seem longer or shorter depending on your inertial reference frame, and this space metric, which can be different based on your inertial reference frame. This, however, this delta tau, this proper time, and this proper length are both what we called we just said the word for it a minute ago. They are I forgot what the things are called. Dang it. I had something. They're called invariance. Invariance. So proper time and proper distance, delta tau and delta sigma, are both invariants. What that means is, even though two observers may have physically different times or physically different distances, that their proper times, their proper distances will be the same. If they use one measurement frame, they will be able to measure accurately in reference to one another. So that being the case, we're going to dive into even more examples of that. Thank you very much, guys. We have 2 likes going on. Let's see. Ooh, this live chat is blowing up. Y'all are killing it. So, I don't know if you all can see this here, but I hope you understand the concept that I'm trying to get across. The thing that's exciting about all of this, the thing that makes it interesting, and maybe I can kind of get a better angle there, is that this is describing actual changes in the stretching and compressing of space and time. So we now, by being able to find constants or invariants within the math of describing differences in space and time, that initially threw us for a loop. Before we had these invariants, we didn't know how to measure if these things are relative to each other. But just as quickly as the problem was brought up, it was solved with these invariants, which said, hey, not only is this difference between these reference frames a problem, but it also provides a solution. And that's what these invariants are. So you can actually calculate the differences between your change in time in different reference frames, what the different reference frames characteristics are relative to one another based on using invariance. And that's an exciting concept. You can even get that from things that become paradoxes, like this twin paradox, is how did one twin experience 5 years while another twin experienced 4 years, and they've changed in age relative to one another even if they were born at the same time. That's what we talked about a minute ago. We're about to look at another one that is just as interesting, where we have a particle that's going toward a detector, and we have to try and figure out whether or not this particle is going to reach our detector. It decays at some specific half-life that is, in first thought, too far to reach our detector. That our detector is a far enough distance away where the particle will decay once it comes out of this particle accelerator and not reach our detector, so we won't know whether we actually made the particle or not. A way we can fix that and figure out whether it's true or not is by using our delta sigma, or our specific length. So we can measure that in time as well. So let's say we have our particle accelerator, and it is emitting a muon. A muon, which this is the symbol mu, a muon that decays at some specific half-life, let's say a distance of, let's say it decays in a time of 3 seconds. Really? Yep. Decays in a time of 3 seconds. So then it decays in a time of 3 seconds, and if we measure with light, if we were to take the time that it takes for light to go from that point on our detector, the same point where this muon will come out, to our detector, we know that the distance, so this would be our delta t, equals 3 seconds. Our mu decay, our muon decay, which is 3 seconds from the detector. So once this muon is going to be traveling at the speed of light, or near the speed of light, and if it goes for 3 seconds, it will disappear. It will no longer be a muon, and you'll never know you had it. So also, thank you guys so much for the 2 likes. So that being the case, if we have here our decay distance is 3 seconds, and our detector, based on the speed of light, is 4 seconds, you would say, well, there's no way that my particle, mu, will reach my muon particle that decays in 3 seconds, could reach my detector, which is 4 light seconds away. However, we may be surprised by that, because we say we have to first find our invariant, our delta sigma, our what's called our proper length. So our proper length is equal to delta sigma squared, which is equal to our delta x squared, which we said was the amount of time in light seconds that it took to reach our detector from the spot that we're going to be shooting our muon off of, which will be 4 seconds squared. And then we are going to take our time variable, which is going to be the amount of time it takes our muon to decay, which is 3 seconds from the detector, or 3 seconds from the particle accelerator, 3 seconds squared. So we solve that out, and we end up getting a delta sigma squared of 16 square seconds minus 9 square seconds. And we come out with a delta sigma squared that is 7 square seconds. Okay, so from there we can do the square root of both sides, and we can say that delta sigma is equal to root 7 seconds squared. And that's the same for both our light and our muon. So we're dealing with relativistic effects because our muon is going at near the speed of light. That being the case, we see here that our delta sigma is equal to root 7 root 7 seconds. So that is the proper length, root 7 seconds that it should take for the muon to reach the detector. So it's what this is describing is actually let's see what root 7 is. Hold on. Square root of 7 would be 2.645. seconds. So when we compare that to our 3 seconds, we see that delta sigma is less than delta t, which means muon reaches detector. So, the exciting thing about that is you say, well, okay, so you proved that your proper length is shorter than the time that it takes for your muon to decay. Well, what's so interesting about that? We've said that our particle detector is 4 light seconds away. We said our muon traveling at the speed of light comes out and has a decay time of 3 seconds. Once it gets 3 seconds off of that particle accelerator, it decays. We can't detect it anymore. So we're saying that because of relativistic effects, because it's moving so close to the speed of light, it doesn't feel 3 seconds. It actually feels 2.64 seconds of time. So the actual length of time for it relative to you as a person who is not moving at that fraction of the speed of light is longer. It takes longer for a second to pass in effect for this muon. So that being the case, it does not decay because it's able to reach its detector. And that's some of the beauty of special relativity, is that it allows us to do things that we don't always think are possible when we have one specific reference frame that we're holding in mind. This allows us to unlock every inertial reference frame and to understand them relative to one another. And that's what makes special relativity so dang cool. So let's see. Talking a lot about stuff in the comments. Thank you all for the 3 likes, 5 concurrent viewers. I appreciate it. If we can get it up to 5 and 5, I would love that. So right now we are continuing on with our special rel. Let's see, we've been going for about an hour. We're doing good. Trying to get through this special rel, and then we might talk about some micronational stuff, but we'll see. Sorry guys, I hope you all are doing well. I'm just trying to read this book and get a little better understanding so we can continue to move on. Are you guys just getting into a fight about micronationalism? I'm trying to figure out what y'all's game is here. Y'all didn't come here for the special relativity, because that's what we're doing. All right. So, delta sigma squared equals delta x squared minus delta t squared. So, we are talking about our proper length here. Right, and so then we end up solving that out. Yep, we solved our muon detection problem. So let's go to somewhere else real quick. Yeah, absolutely. Y'all should hit up this conversation about special relativity. I hope it's keeping y'all entertained. Well, the Republic of Oakland accepts your way of thinking. I hope you approve my way. Had the yeah. Y'all should keep it up. I appreciate it. I'm trying to learn this stuff and trying to use it to help my understanding of the universe, help us to build more stuff, help us to grow. So, yeah. Let's see. I'm gonna go and check a document. There we go. No, sorry, I'm moving you guys around. Trying to find a specific thing. Waiting for my ebook to load because I'm streaming, and it's not loading because I'm streaming. There we go. Okay, so I don't think that deals with that. So I'm trying to find something in my book, guys. Sorry about that. Let's see. Let's see if the space-time metric helps us at all. Let's see if it does. Let's see if it does. Okay. Okay, so what is it actually asking us? So it's asking, show that the chain That's interesting. So what we're going to do in this is we're going to solve, we're essentially going to prove that in any two reference frames, our kinetic energy should be the same. So we can figure out our kinetic energy based on our force, our distance, velocity, all those things from our first introductions into physics we can use to apply here when dealing with our need to solve for kinetic energies. So if we're dealing with two different reference frames, and we're going to say one of them is this and one of them is that. Okay, then we are going to say that, let's see, let's change that to that. Cool. So okay, so let's figure out what our kinetic energy equation is, because I am blanking on it right now. Kinetic energy equation, 1/2 mv squared. So one of the things that you all will notice is that when we do our special relativity, a lot of our equations come from Newtonian mechanics, and there's plenty of good reason for that. We still use Newtonian mechanics to solve for a lot. They are simple but very, very powerful and effective equations, which have given us consistent results and accurate results all the way up through the present day for things within our bounds up to the past maybe 100 years. So and they've been helping us for a few hundred years. So the thing that's exciting about this, or a couple hundred years, the thing that's exciting about this we can solve for excuse me, this bread. We can solve for things that not only have their and we're not only measuring position or time, or figuring out proper time, proper length, not proper distance, we can actually figure out kinetic energy. And then if we wanted to, we could figure out a proper kinetic energy, and we could go on and on and on finding all of these invariants. So, if we know that our kinetic energy equation is 1/2 mv squared, so then Okay. So that those are the same? Is that what it's trying to tell us? Okay. Looking for more things in my notes. Oh no. Let me close out of that. Let me go into modules. Okay, so we are getting down to show that the change of kinetic energy is so that and the work should be the same. Alright guys, well, I know we've gotten into a lot today, and I imagine you all are just about full of special relativity for the moment. I hope you have learned something from this. I hope this is something that was interesting for you. I have needed it to just learn, and I wanted to connect with you all today and tell you that I appreciate you all. We're doing well, we're growing as a community, and I'm excited for where we go. So thank you all so very much for watching, and I will see you very soon in the next video.